All right, so in this video, we're going to just go over the alternating series tests. And it says that if you're given a series that involves -1 to the power of n, or possibly -1 to the power of n plus 1 times a sequence, an, where you know that the sequence terms, an, is always going to be positive, then your given series will converge if these two conditions hold. The two conditions is that first, when you compute the limit of the sequence, it must be equal to 0, and sequentially, as you choose values of n, as n is equal to 1, 2, 3, so forth to infinity, sequentially the terms are decreasing. But they're all decreasing, but yet just keep in mind they're all positive. All right. So here's our first example. We have the series from n equals 1 to infinity of -1 to the n times 5, they're all divided by 7n plus pi. So two things we have to check, right? So we have to check limit and sequence terms. For the limit, it must be equal to 0. Well, let's see what happens. Well, you define your an to just be 5 over 7n plus pi. In other words, you just disregard the -1 to the n. And if you disregard it, you have your sequence. So let's compute the limit. What is the limit as n approaches infinity of 5 over 7n plus pi? Well, as n approaches infinity here, 7n becomes infinity. So 5 over infinity is what? 0. So the first thing is check, right? I'm going to put a check mark on the limit. We see that the limit is indeed equal to 0. So that's good. Now the second thing has to be true, is that when I look at the sequential terms, it must be decreasing. Well, let's write out a couple of the terms. You have a1, a2, a3, a4. So the first term will be 5 over 7 times 1 is 7. So 7 plus pi will give us 7 pi. Your second term will be 5 over 7 times 2, which is 14. So you get 14 plus pi. Your third term is going to be 5 over 14 plus, no, sorry. 7 times 3 is 21. Blackjack. Yep. So you get 21 plus pi. And then you get 5 over 7 times 4, which is 28. So it's 28 plus pi. So sequentially here, what you can see is that A1 is definitely bigger than A2, which is bigger than A3, which is bigger than A4. Right? So the sequential terms are decreasing, right? Right? The AN terms are decreasing. So therefore, by the alternating series tests, I'm going to abbreviate it, alternating series tests. You could call it AST if you like. Our given series converges. Again, I can't stress enough that you got to show that the limit is equal to 0 and that it's decreasing for all n. But you can see that the pattern is going to hold essentially here for the decreasing part. So that would be an example of an alternating series, but I think I could come up with another example. In the chat, I said, you said, let's just say we made the numerator an n here, right? Or 5n. If I try to do example number 2, let's say we have n equals 1 of -1 to the n power of 5n over 7n plus 3. So I'm going to remove the pi part because I want to do the computations just to see what these values would look like. Okay. So for this series, you have to define your an. So what is my an in this example? What is my sequence? That's right. You have 5n over 7n plus 3. So if I compute the limit here as n approaches infinity of 5n over 7n plus 3, that is equal to what? Yeah, this will be 5. Hey, excuse me. Hey, excuse me, sir. Hey, excuse me. This will be 5 over 7. So since 5 over 7 is not equal to 0, then the first condition in terms of the limit doesn't hold. So this series will diverge, right? So by the alternating series tests, our series diverges. Do I need to check that the sequential terms will decrease? No, I don't need to, because in order for you to have convergence, both conditions must hold. If one condition fails, it's automatically a divergent series or divergent alternating series. Okay. So I don't have to actually check that. All right. So I'm going to stop there.